In this video, we want to take a look at equations of lines and finding equations using the dot product. First of all, I want to remind you of what an equation of an object is. If you've got some object you're trying to describe by an equation, you're trying to find an equation in terms of the variables x and y, since I'm working in a plane, that is true if xy is on the object that you're trying to describe, and is false if xy is not on the equation you're trying to solve. So for instance, the equation x squared plus y squared equals 25 is supposedly describing this circle here. Well, if I take a point that's on the circle, for instance 3, 4, 3 squared plus 4 squared, 9 plus 16 is 25. That's a true statement, so the point 3, 4 is on that circle. If I took the point, let's say 3, 5, well, 3 squared plus 5 squared is not equal to 25, and so it's not on the circle. So every point on this circle, it turns out, the coordinates satisfy this equation, and every point off don't satisfy the equation. And I point this out just because sometimes I think we forget what it is when we say find the equation for something. We're trying to find a statement that is true if and only if the point xy is on the thing we're trying to describe. Okay, so we're trying to do lines in R2. Okay, so here's what we're going to do. It's going to be a little bit different starting point than what we've done before. So I want to start with a point, x0, y0. That's this black dot here. This is the point. Oops, this is the point. Where's my x0, y0? And I have what I'm going to call a normal vector, and that's the vector AB. That's this vector right here. And I've also drawn it translated over to here. That's the vector AB. Now, normal vector. The word normal is used way too often in mathematics, and it means different things. For instance, the book is already, I don't think I've mentioned it in a video, but the book talked about normalizing a vector. Well, to normalize a vector means to make it a unit vector, divide by its length. But when we talk about normal vectors, we're talking about vectors that are perpendicular to things. So I generally try not to use the word normal to mean unit vector, try to mean perpendicular. But anyway, here's my normal vector. I want a line that goes through this point and is perpendicular to that vector. So I have the line dotted in there. This is supposed to be a right angle right here. Okay. And I want to come up with an equation for that line. So what I want to do is I want to find an equation that's true for every point xy that's on that line, and it's false for every point that's off the line. Now, notice, if this is supposed to be perpendicular, then the vector from here to there should be perpendicular to AB, and I've got a way of describing perpendicular vectors now because I know that perpendicular vectors have dot product equal to 0. I have an equation that describes perpendicularity. Right? So the thing is, how do I get that vector? Well, if I think about the vector here, let's just call that capital X0, and the vector here, that'll just be capital X, then the vector in between those would be x minus x0. These are capital X's as opposed to the little x, which is the component, the x component of capital X. So this vector is supposed to be parallel to that line. If xy is on the line, then it will be parallel to the line. If xy is off the line, it will not be parallel to the line, and it will not be perpendicular to AB. So what I want here, this is vector n, what I want is that this vector right here is perpendicular to n, so that the dot product with n is equal to 0. And so that is what I now do right down here, that the vector x minus x0 is you just subtract the x components, you subtract the y components. That's this, and I want it dotted with n. I want that to be 0. This will be true if xy is on the line. It will be false if xy is off the line. So what I have right there is an equation for the line. Now, it's not an equation that we generally look at, but this is really the This is a vector equation for the line. It's certainly an equation involving vectors, but it involves the coordinates x and y. And it's true if the xy is on the line, it's false if the xy is off the line. So it is an equation for the line. Now let's just see what that looks like in terms of equations maybe we're more used to looking at. Right? So the vector n is AB, and so I'm going to dot AB with that. And so the first components get multiplied, the second components get multiplied and added. That's still supposed to equal 0. This right here is what I would call the point normal form for the equation of a line. That is, point normal, meaning you can clearly see the point that the line goes through, x0, y0, and you can clearly see the normal vector, AB. Right? That the components out in front here are the a and the b, and the x0, y0 are the point that it goes through. Now just multiplying this through here, distribute the a, distribute the b, looks like that. Move this over. This is another form that you see quite often. Ax plus by equals stuff over here. But that stuff is all numbers that are given, right? We're given the normal vector, AB. We're given the point we want it to go through, x0, y0. So this is all going to just be a number. And a and b, of course, are numbers, so x and y are the variables. And you have an equation that looks a lot like equations that we've been dealing with, in solving systems, for instance. But also written like this, it brings me back to the vector form. The left-hand side here is just the dot product of AB with XY, and the right side is the dot product of AB with X0, Y0. So this is n dotted with XY is equal to n dotted with X0, Y0, which is kind of interesting. Let me slide back up here a little bit. This is saying that the points on the plane, the points on this line are the same points, xy, whose dot product with n, or either that n or you can think of this n, that this x dotted with this n is the same as x0, y0 dotted with that. Somehow that seems to maybe be related to, because of course n is perpendicular here, somehow it seems like all of these points, if I projected them down perpendicularly onto that direction right there, that they'd all end up in the same place. So somehow, maybe the dot product is related to projecting. It's not exactly the projection onto there. We will see projections in a subsequent video here. But it is curious that one equation for that line is that all the points in the plane that are on that line are precisely the points that when you dot them with that normal vector, it's the same as dotting the given point with the normal vector. Let's do an example. Find the equation of a line through the point 4, 1 with normal vector 1, 2. So just using the formula that we just had here, the point normal form, the normal vector is 1, 2, and the point that I want it to go through is 4, 1, and so I have that. I've got the equation of the line. And you could leave it like that if you want. Notice I didn't say find the equation, I said find an equation. There's lots of equations that describe this line, and this is one of them. This is one where I can clearly see the normal vector and the point that it goes through. Just because I want to see that it really is the line I expect, or that it satisfies the properties here, I'm going to distribute the 1 through and the 2 through and get this to look like I'm used to seeing, y equals mx plus b. Right? So I can see that this line that I came up with, the equation that I came up with, was describing, in fact, this is exactly the same example of the picture I drew up above here. The point, even though it didn't, I don't think anything was labeled up above on that picture. No, nothing was labeled. But it's this picture right here. It went through the point 4, 1, and the normal vector was the vector 1, 2. And so I can see that blue line, which is perpendicular here. It's got a y-intercept of 3 and a slope of -0.5. So yeah, I do have a line through this point that's perpendicular to that line. One of the things I know about slopes of perpendicular lines from previous course is that where this vector has the slope of a rise of 2 and a run of 1, so this has slope 2. The perpendicular slope is the negative reciprocal. So the reciprocal of 2 would be a half. This has to have slope minus a half, and in fact, it does. Okay. One more thing I want to do is just to go backwards here, and I say, what do you suppose, I showed the answer here. What's the normal vector of this line? Here's the equation of a line. Can you see the normal vector? And the answer is yes, you can clearly see the normal vector because the coefficient in front of the x and the y are the components of the normal vector. So I don't see the slope so well on this one, but I see that it is perpendicular to the direction 3, negative 4. 1, 2, 3, 1, 2, 3, 4. So that direction right there, the line is perpendicular to that. Now I would need to know a point that it goes through. I happen to see the point 1, negative 1 works. So this point right here, perpendicular to that direction there, and I have that line, the graph of that line. Okay. The dot product gives us a way of making an equation out of the statement two things are perpendicular to each other, because those two things, those two vectors would have a dot product equal to 0. Equal to 0. I have an equation.